Okay, so hi, I'm Sumo. I'm representing my team solution in this competition. First of all, as always, thank you for the host, and also thanks for my friends for all these experience. Let's move on. So our agenda follows the usual flow, which is the background summary, how we process data, how we train model, and what are the important findings or ablation studies on how to simplify our solutions down. So yeah, so first of all, background, which is where each of us come from. Because all of our members are in here, I'll present myself and then I'll pass around to my colleagues to present themselves. So as for me, I'm Sumo. I've been working for 5 years now as software engineer mainly, with some years being a machine learning engineer. I've joined a couple of Kaggle competitions in the past that I believe helped me in this one. Next, I'll pass on to Sahil and then around.
Yeah. Hello, everyone. Thanks for hosting this competition, first of all. And yeah, I'm Sahil, and this was so I used to work as a Haskell developer, and now I'm pursuing my bachelor's in data science. So yeah, thanks for hosting the competition again.
Naoki?
Okay, I'm Naoki Hashimoto. Sorry for my name is displayed in Japanese. I'm also known as ITK 8191. I've been assigned to work at the Japanese branch of certain American company, where I'm responsible for system maintenance and operation as well as connecting with this with AIs. And my company does not have a system for promoting Kaggle, but I'm so study computer vision and signal processing as a hobby. Thank you.
Finally, it's me. So my name is Sergio Alvarez. I'm a master's student in computer science, and I also work as a backend developer at a local company here at Brazil. And my master is focused on automating quantitative and morphometric analysis in images from the enteric nervous system. It's very different from the images that we were working on, but at least I had some experience in biological images.
Cool. I'll move on to our presentation on our solutions. So this is basically the summary on what's actually going on when we submit our models. Our models consist of 3 main types of models, with the main difference being their sizes and some other small differences. With an ensemble of our models together, each models are 3D segmentation models trained with similar parameters or hyperparameters. We average everything by the logic level before we do our processing to get out the coordinates of each particles. Along the way, we did find some interesting inference tricks that we call it, and then we will present these tricks in our subsequent slides. But the takeaway is that we submit an ensemble of segmentation models. All right. So we use our standard tools. We base our models off of Monai. We train everything with PyTorch Lightning, and we post-process with GPU accelerated stuff like QPy and QSIM, which will be outlined in the following slides as well. So first of all, how we pre-process and how we augment our data. So we pre-process our data by just taking the tomogram, and then we take the interest radius of each type of particle, times it by 0.8, and then that basically becomes our segmentation binary mask. So this means each tomogram will have a segmentation mask with binary labels with each of the classes, including the background. And during the training, we did try out a lot of augmentations, but unfortunately, none of them actually works. And the one that sticks with us are just 3 of them, which is flipping along each axis. So flipping is basically like we just mirror the tomogram around specific axis. Next, the training methods. So we base our models on units of Monai, which is the vanilla unit with some monite flare on top. And then we did try it out with different sizes of units. And the one that sticks are 3 of them, which is the tiny one with 1.5 million parameters, and the medium one with 4.5, and then the big one with 11.8. One thing to note here is that even with the big one, the number of parameters are still quite small. This is because our finding aligns with the other teams that big models doesn't really work that well, potentially because they just all overfit. Next, I think this is one of the main difference that we take compared to other presentations that we have seen so far, which is for each of the model size we assemble together. Before we train with the real data, we take them to fine tune with synthetic data. We find that doing this allows the model to converge faster on the real world data and also reach a little higher validation score during the training. So the way it goes is that tiny and medium units are pre-trained on these synthetic tomograms. Each of them are trained with 7 synthetic ones. And then the big units are pre-trained with all 27 synthetic tomograms. And we did some little pre-processing for the synthetic tomograms by Gaussian denoising each of them. And we think visually this leads to better signal to noise ratio. So for example, we have this image here, which is rather noisy. We did some Gaussian denoise, and we think the particles are more clear to us. And then we derive some labels from it that we use to train the model. Right. So after each model size is pre-trained with the synthetic data, we then fine-tune them with these hyperparameter configs, which is pretty much the usual 7-fold training model with Adam W with this learning rate of 1e to the power of -3. We use the CZII loss, which is pretty much weighted average or weighted sum between the dice loss and cross entropy loss. We did use the usual bells and whistles, which is to reduce the learning rate on plateauing. We used some exponential moving average with details on subsequent slides to try to stabilize the final output. And then we use the early stopping with asset patience. Okay. For our EMA scheme, we did use the momentum of 0.01. This means on each of the back propagation step, we update the EMA's weight by this formula, which is stick to 99% of its previous weight and take the rest 1% from the new model. We did something we called the warm up, which means that for the first 100 gradient steps, we just take the momentum being 1.00. We think this saves us a bit of time during the first iterations where the EMA model and the models are quite different and models are changing a lot during the first few epochs. Okay, now comes the next rather interesting part. So after the steps on the previous slide, we would end up with a 7-fold model. And with this 7-fold model, it would run out on the inference time. So we did this trick called a model soup, which is basically taking the 7-fold model, take their model weights, average them together, and then we end up with one single model that we can use. We think this sounds weird at first, but it actually works out really, really well for us. So by doing this, we kind of condense all 7 models into one final model that actually performs much better than submitting only one fold. So for example, this for the medium unit, we saw quite significant boost in terms of the leaderboard scores that we are getting after doing this trick. And then this saves us a lot of inference time. Okay. After we have our model soup and our 7-fold model, we pick some hyperparameters by the usual steps of just comparing the out of 4 scores, or in the case of model soups, we just claim that it's okay for it to leak data. The score will be very inflated, but it would still have some signal for us to pick the correct post-processing hyperparameters or some other parameters that we are tuning. Once the model soups are submitted to the kernel, and once their final scores are averaged into one heat map, we do this GPU accelerated post-processing on the heat map to get our final coordinates, which is basically taking the heat map and then we threshold it into a binary mask. And then we do our watershed segmentation, which is to first compute the distance transform of the binary mask, pick the local max, and after we get the local max, we run this watershed segmentation algorithm to get the volume occupied by each particle, and then we throw out the volumes that are too low in terms of voxel count or too small, and then we end up submitting the centroid of each segmented cluster as our final solution. So that's pretty much our entire pipeline. And here we will go through each of the interesting findings we think we see along the way. So the first one is the model soup that, as previously mentioned, we think it helps us a lot in terms of getting where we are today, and while maintaining the same one-fold inference time. So the plots we show here is each configuration or each of the 7-fold we have. And the red star here is the score of the model soup. As we see, the model soup scores like higher than each of the fold. The second thing we do is that we do this bigger patch inference, which means the model is trained on one patch size, which is 128 cubes. But then we submit during our inference time, we run the model on a much bigger patch size. So for example, this model is trained on 128, but then when we go and submit, we use this patch size instead, which is much bigger than the one it was trained on. Doing so gives also quite significant boost in terms of the public leaderboard and also the private. We saw 0.01 boost by doing so. I think I clicked on the wrong place. Okay. So the second one is that the tiny unit or smaller units models are the better. During the beginning of the competition, we tried really big models, and our score plateaued around 0.74. Once we switched to the smaller ones, even with the same inference time, we can ensemble more of them. And this is the first time we exceed this wall, and then we start working towards this area more. Miscellaneous. So only flip augmentations work well for us. Here are the other lists we have tried, and none of them really worked. And also, we found out that training some models, because we submit 4 models in the ensemble, having some of them being trained with EMA and some of them being trained without EMA leads to better scores. We think this is because the models in the ensemble ends up being more diverse. So we stick with that as well. So that outlines our solutions, and here's our ablation studies in terms of how much training time or inference time we can shave off and how much impact that has on the leaderboard score. So our baseline has 0.77 on private leaderboard. If we don't do the big patch inference and we just use the training patch to inference, we got quite a significant impact. If you do not do any test time augmentations at all, we get somewhat a small reduction in the score. And here we present what happens if we don't ensemble at all, and we just submit one type of model, and the reduction are as follows. But the bottom line of this is that if you were to submit only one model, the best model to submit is probably the big unit trained on all types of tomograms data, because that would lead to the minimal impact on the leaderboard score. Yeah, so that's basically it for our team. In conclusion, we did ensemble 4 different unit types with 3 different sizes. all models are trained on synthetic data and then fine-tuned on the real one. Sevenfold models are converted into model soup, and that leads to better leaderboard score with the same inference time. And we post-process using watershed segmentation. We find that model soups is kind of cool. Big inference patch is quite nice. Small units are better, at least in this competition. Augmentations beyond flipping doesn't really work for us. And ensembling models where some are trained with EMA and some aren't actually leads to better scores. That's it for our team. We'll move on to